Hello and welcome. My name is Peter and today I'm going to be talking to you about my final year project, where I use the Julia programming language to simulate molecular dynamics. What does that actually mean? Well, molecular dynamics is the study of how atoms move and interact with one another. By studying this, researchers can gain insight into interesting phenomena such as how matter changes phase with temperature, or how a solid may react to an impact, be it deform or fracture. Now that we've talked about why it's useful, we can talk about how it actually works. So, molecular dynamics is the study of motion, and it's done using classical physics, which means the backbone of this project boils down to Newton's second law. And this states that force is equal to mass times acceleration. As it's a computer simulation, we need to solve this for a finite number of discrete time intervals. And to do this, we're going to use the Verlet equations shown here. What these equations tell us is that we know where an atom is going, depending on where it is, where it's been, and how much it's accelerating for a given time step squared. And once we know where it's going and where it's been, we can calculate a velocity. So, before we can get up and running with our simulations, we need to find this acceleration term. And with the second law, we know its acceleration will be based on its force. As you should already know, atoms can behave very differently depending on what they're interacting with. Sometimes they can be highly explosive, sometimes they can be seasoning. So we need to decide for our simulation how our atoms are going to interact, and to do this we're going to choose what's known as a potential. This is a function that will determine the force acting upon an atom depending on how the atoms are arranged. For this project, we're going to use what's known as the Lennard-Jones potential. If we take the case of two atoms, we shall assume they have full outer shells, so we can ignore the issues of bonds forming. Now we know that the negative charge of the electrons will be attracted to the positive charges of the nucleus in other atoms, so they're going to want to move close together. However, as they get close, the negative charges of both atoms' electrons are going to repel one another and force them apart again. Now this is the motion that is described by the Lennard-Jones potential, and that can be represented by the following equation. In this, V is the interaction potential and R is the separation. Epsilon and sigma are properties of the material being simulated, and they'll scale the interaction. Now when using the Lennard-Jones potential, it's common practice to assume these have a value of 1, as these ensures all values measured will have the same scaled units. Now we can see the potential is made up of two reciprocals, 1 to the power of 12 and 1 to the power of 6. We can solve this equation for a wide range of distances and produce the following graph. This summarizes that at close distances, the force of the atoms will be extremely repulsive. As they separate, it will become slightly attractive before tending towards zero. Now in our simulation, we can save a lot of time calculating if we assume that at a distance greater than 3 units, the force will just equal 0. By putting these equations together, we have a system that can simulate molecular dynamics in one dimension. Here we can also see a fundamental part of the simulations, the boundary. In our simulations, we have 10 atoms in a box. In a physical realm, that is absolutely tiny. Not only that, but any walls of the box will have an effect on the atoms. Therefore, we're just going to assume they aren't walls at all, but rather they're periodic boundaries. Meaning, we assume our box is surrounded by an infinite number of identical boxes. So if an atom was to cross the boundary, an identical copy is going to enter from the other side. And that means the amount of atoms in our simulation will always be constant, and we can assume that our box is representative of a much larger scale of atoms. Typically, the scale of atoms in a simulation could be limited to, say, 10 to the 3 or 10 to the 6 atoms, and this is just down to a limit of computational intensity. It simply takes too long to simulate anymore. Now that we actually have atoms moving, we can start measuring velocities. And once we have a velocity, we can measure kinetic energy, as that is simply a half by the mass by velocity squared. Once we have the kinetic energy, we also have the temperature of the system. Now, we're calculating the velocity by measuring the distance travelled across 2 time steps. If we were to scale up that distance travelled by a set amount for each atom, what we've essentially done is increase the average velocity, which increase the average kinetic energy, which thus increase the temperature. This scaling method is how we're going to introduce heating and cooling elements to our system. To demonstrate this heating effect in action, we're going to place 16 atoms in a square lattice. these atoms have been given a very low starting initial velocity. As they move together, they'll begin to equilibrate. However, once we start to implement a rescaling heating effect, we can see the atoms' interactions become much more energetic. This motion gets more and more exaggerated as time goes on due to the effect of extra external heat flow. From this we can see we've heated our starting solid into a fluid state, as the atoms are not following any general pattern, they are simply free to move around. This effect can also work in reverse. In this scenario, we've started our atoms with a very high initial velocity, and we can see they're in a very fluid state as the atoms can move anywhere within the boundary. However, as we begin to cool them, we can see the amount they move becomes less and less. Rather than travelling the entire boundary, the atoms begin to find a distinct region at which they'll stay. This is their position in their lattice structure that they will finally be frozen into as a block of ice. Just like that, we have a block of ice. Or more accurately, we have a target that we're going to launch a projectile at very high speeds. Now to do this, we're going to model cannon fire. So this is best described as a very high initial velocity and is affected by drag and gravity as time advances. It can be better described with these three equations. So let's examine these in detail. The next location of the projectile is dependent on where it currently is, plus its velocity by a time step. Now, the drag it's experiencing is dependent on a property B2. Now this is derived from the shape of the projectile. It is almost impossible to calculate, so it's always approximated. And for our large cannon shell, we're going to take a value of 4 by 10 to the minus 5. The drag is also then going to be affected by the mass of the projectile, its total velocity in all components, multiplied by the component of the axis we're dealing in, so be it horizontal or vertical. Finally, its next velocity is going to be dependent on its current velocity plus the drag by a time step. Now it's important to remember, when we're dealing with the vertical axis, we're going to subtract a value of 9.8 every time step. And this is to add in the effect of gravity on our projectile. And now, let's take a look at this in motion. In this simulation, we're launching a blue bullet at high speed towards a block of ice. We can see that as the bullet hits the ice, the projectile atoms get embedded deep within the block. This impact causes an extreme deformation to happen to the block. As it collides, we can see a vacancy that is left in its wake. This vacancy expands as the bullet lodges deeper inside the block. This effect ripples through the block of ice, and we can see it has effectively been vaporized from the impact. Moving on to 3D, we have created a spiked projectile for this simulation. This projectile will be launched into the air and will fall down and attack the block of ice from above. As it hits, the projectile is flattened from the impact with the block of ice. It causes a major disruption to the top layer of atoms of the ice block. These atoms are launched and break free of the lattice structure of the block of ice. The projectile atoms themselves can be seen to recoil upwards. As time advances, the damage propagates through the rest of the ice structure. And with that ballistic scenario, that's our project finished. All brief objectives have been met. But the one thing we haven't talked about yet is the performance of the code. And more importantly, how do we improve its performance? I compared the code I wrote to an open source simulator called LAMPS. Now LAMPS was originally written and is still maintained by a company called Sandia. Now Sandia used to be called Los Alamos. You know, that Los Alamos. So it's safe to say they know a lot about atoms, and it really shows as they won the drag race benchmarks that I ran, hands down. But what it did was give me inspiration for how to improve my own performance. You see, LAMMPS uses multi-threading, allowing it to solve the Verlet equations for multiple atoms at a time, thus greatly cutting down the time spent simulating. And this is something I implemented in my own system. I used a threading macro to allow me to run multiple steps of my for loops at a time, fully leveraging my CPU and cutting down the time spent simulating. However, it's only in the last few years that CPUs have come to have double-digit cores. So there's really a limit to how far we can go on consumer hardware. Although, there is an alternative. You see, there's another component in a computer that has thousands of cores, the GPU. And although these are much slower than a typical CPU core, the sheer bulk of them should allow them to race faster. And the Julia programming language supports running code on GPUs. So, I restructured my code to run on a GPU instead of a CPU. And when I ran it in a small-scale simulation, it got absolutely destroyed. It has no match for the faster, fewer CPU cores. But things started to change once I increased the amount of atoms in the simulation. Once the number reached a high enough value, it was able to fully leverage all of the GPU cores to complete much quicker than any CPU could dream of. This speed boost opens the door for larger scale and longer duration simulations. In conclusion, I set out at the start of this project with the end goal being to have code to simulate molecular dynamics and to investigate a scenario where a projectile is launched into a block of ice. Now here we are at the end. That system has been built. It can simulate molecular dynamics in 1, 2 and 3 dimensions, and it works spectacularly and has yielded plenty of results that were analysed in detail in my report. The performance of this code was measured and evaluated and compared to an open source existing solution, and finally it was restructured to allow it to fully leverage the power of a GPU instead of a CPU. In future, this code could be expanded to include different potentials, such as the Tursoff potential. Now this accurately describes the interaction between semiconductor materials, and if we were to combine that with the ballistics created in this simulation, we could begin to model the diffusion of dopant atoms into a silicon wafer. This is the end of my presentation, so thank you all very much for listening.